So when we adjust our window a little bit and start x at 0 up to 10, and let's just set y min from 0 to 300. Now, we know that the y's, that the range of y's cannot be negative, since the square root of a number will always be a 0 or more. Now when we take a look at the graph, we notice that it's very similar to our sketch. One little interesting tidbit is, depending on how strategic we are about picking our x's, let's say we were just studying the square y equals the square root of x. So for an input of 1, we get a perfectly even square root. The square root of 1 is 1. Now I have to increase my x all the way up to 4 in order to get another perfect square root. Then I have to increase it to 9, where the square root of 9 is 3, 16, because the square root of 16 is 4, 25, and so on. Square root of 25 is 5, and I'm picking these because I notice that the change in y is uniformly equal to 1 as long as I pick numbers whose square root is perfectly even. But notice how much I had to increase x by each time in order to be able to get this. So for initially, in order to get an increase in y of 1, I had to increase x by 3. To get y to increase by 1 more, I had to increase x by 5. And so you're probably, hopefully, seeing a connection now between square roots and squares. Well, we know that the opposite of a square root is a square. So if I squared both sides of this thing, y equals the square root of x, and I squared this side, and I squared this side, I would have y squared equals, well, the square root of x squared. If I square root a number and then I square it, I get the original thing back. So in this case, y squared would equal x. So it is related to a quadratic. In other words, if I increase y by 1, 2, 3, 4, 5, then I'm going to be able to produce the x's on this side. So there's a relationship, and the relationship is quadratics and radical functions are inverses. So that's a term you'll discover later on in math, but for now that's just the connection that we want to make. So let's think about the domain and range of these functions. So domain, remember, refers to the values of x that can be used. Now I know I can't take the square root of negatives, and so that tells me that x has to be bigger than 0 or equal to 0, since 0 times 0 is 0. So I can basically put anything under this radical unless it's bigger than 0. So that's why when we look at our graph, we notice that even if we do go into the negative territory, and even though we would go into, like, let's say negative 100 here, we're not going to see anything because this function doesn't exist outside of the first quadrant. This function only exists inside the first quadrant, at least the way it appears. The range, well, since the square root of x is, since we can only put in positive numbers, we can only get positive numbers out. So the range would be y is greater than or equal to 0. Again, if we put in 0 for x, we're going to get 0 for y. So hence we get something that only exists in the first quadrant, where x is positive and y is also positive. So positive, positive. What about looking at a function like y equals the square root of x minus 3? Well, the question to ask ourselves is, we want to make sure that this number is bigger than or equal to 0. So let's just graph it real quick. If I put in the square root of quantity x minus 3, then I'm going to set my zoom to standard again just so we get the nice window out. Notice that it starts at 3 and it kind of has the same shape, except it starts at the point 3, 0 and then continues on. Well, x minus 3 is equal to 0 when we add 3 to both sides, or you can probably see it, when x is equal to 3, the quantity under the radical is going to be equal to 0. So if I make x any smaller than 3, like for example, if x is 2, then that means that x minus 3 will be 2 minus 3, which is negative 1. So in other words, if I put in 2 for x, I get the square root of negative 1. So anything under 3 will give me negative values under the radical. So that must mean that in this case the domain would be x greater than or equal to 3.